Welcome everyone to OChem 1 Exam 2 review. Here's a list of stuff that we're going to be covering today in order. My hopes with this review, it's kind of early, you might have noticed, but I'm hoping that if there are things that you have not yet covered in class, then I can kind of expose you to the information beforehand so that it will be easy to learn. But if you've covered like most or all of these, then I'm hoping to help reinforce that information. By the way, if you're here for certain things, like if you're here specifically for E1 and E2, like these two, but you don't know about alkenes, things might not make sense, right? So my recommendation to you is to watch this in order at 2x speed or 3x speed if you have that YouTube feature. Um, because I placed this in this order because everything builds off on the previous thing to an extent. But it doesn't really matter. If you come across something that you're not sure of, you can always go back and refer to it. I also want to mention that it's good that you're here because I mentioned a lot of like obscure things. For example, PBr3 and SOCl2. If you know about these, good job. But if you don't know, it's good that you're here because some of these things are barely talked about in class, and I'm going to, bring it to your attention so that you know and you won't be scared when you see these. And just in general, this will be over everything that you need to know for your exam. Um, there will be times where I explain a little bit extra, but I'll like emphasize how questions will show up on your exam. So for monohalogenation, I'm just letting you know right now, I will be explaining a lot in terms of how it works, but it's not going to be that big of a deal. It's just for your understanding. What actually comes up with monohalogenation will be very light. Okay. And one last thing, if you've been coming to my sessions, you already know what I'm about to say, and you're probably very tired of me saying this, but I'm going to say it again. Big disclaimer, if I say anything that is opposite to what your professor says, do not listen to me, okay? Just ignore me, because ultimately your grade depends on what your professor thinks. And don't worry, okay? This difference in opinion stuff only comes up over here and potentially over here, but it's generally for SN1 and E1. When I come to this section, I'll tell you what there are differences of opinion in, but you're chilling, don't worry too much. So let's begin. The first thing we're going to talk about is cation, anion, and radical stability, and we're mainly referring to carbocations and carbanions and radicals because that's like what we're dealing with at the moment. So when it comes to carbocation stability, the ranking is going to be like this. Tertiary is better than secondary, is better than primary, which is better than methyl. But we also have benzylic and allylic right here, right? Benzylic and allylic are better than the rest. And this is its own category, right? These are resonance stabilized options. So when it comes to tertiary, it would look like this. Secondary would look like this. Primary like this. And methyl would look like this. It could also be, something like that. But what do these numbers mean? With your carbon or carbocation in question, look at how many carbons you're bonded to. Okay, we're bonded to 1, 2, and 3, which means this is tertiary. The second one is just bonded to 2, so it's secondary. The third one is bonded to just 1, so it's primary. And what about these last two right here? They're bonded to like no carbons, right? So instead of 0, we just put methyl because that's like another way to say it. CH4 is a methane, so bonding to no other carbon is methyl. And this is like the best example of it, right? Just hydrogens. When it comes to B and A, benzylic looks like this, where you're able to do resonance with a benzene. So something like that. And then allylic, here let's write primary benzylic. allylic will look like this, where you're resonating with just a double bond, not necessarily a benzene ring. So this one would be primary allylic. And you want to make sure that you're one away from a double bond, right? We're one away from double bond or benzene, because then you're able to actually do resonance. So for example, right, you can resonate like this and get this structure here, and then you can continue and so on. For this one, same deal, resonate your double bond and get that. So, that's what you do. And I want you to keep in mind that the worst resonance is better than the best non-resonance. So a primary benzylic should be better than a tertiary non-benzylic, just because we have resonance. So good thing to keep in mind. So this is the first instance of difference of opinion. I think there's one professor that says that a tertiary is as good as a benzylic. I don't really believe that, but just in case, okay, keep that in mind. But generally what I said is correct. Another thing, when you're classifying things, let's say that you have, this right here. You might be quick to call this a primary allylic because this is bonded to just one carbon, but make sure you know the resonance structures. If you resonate this, look what you end up getting. Now you have a secondary allylic. So try to keep the better structure in mind, like the more substituted, because when it comes to ranking, it will help a lot, okay? If you're comparing two of the same thing, like two primary allylics, the differentiating factor will be in their resonance structures, right? So if you get secondary allylic versus primary again, this one will be more stable for carbocations. Okay? Now let's talk about radicals. Radicals are literally the exact same thing as carbocation ranking. So literally, like, Ba 3, 2, 1, M. The reason for this is both radicals and carbocations are electron deficient. Positive charges are obvious. Positive literally means lacking electrons. But a radical, like, think about this. This is a lone pair. If you're removing one, now you're deficient in electrons, right? And radicals literally look like this. It's a dot. Like if you had this is a radical. So the ranking will be the exact same. If you're ever asked to rank by radical stability, you can just like literally replace these dots with a positive charge, if that makes it any easier for you. And the ranking would be the exact same. So keep this in mind. Now I'll explain why this ranking exists, but let's talk about carb anions first, and then we'll do that. So when it comes to carb anions, it's going to be benzylic and allylic again, but the rest of it will flip. So next will be methyl, primary, secondary, tertiary. So, once again, this sucks. This is tertiary. This is pretty good, primary. And this is really good, primary, allylic. So why does this ranking exist? Let's talk about inductive effects. Okay. So your inductive effects, you have two types. You have electron withdrawing groups and electron donating groups. Electron withdrawing groups are good for negative charges, but bad for positive charge. And then for EDGs, they're good for positive charge and bad for negative charge. Just think about it, right? If you have a negative charge and you withdraw electron density, you're basically like neutralizing it. You're pulling away negative charge or negative density. But if you're donating electron density, you're really like, putting a lot of negative charge in one single place. That's why electron donation is bad for negative charges. And the opposite is true for positive charges. If I have a positive charge and I'm donating essentially negative charges, that's neutralizing it. But if I'm withdrawing negative charges, I'm just making it more positive. So I'm localizing a certain charge in one area. That's why this exists. Now, some common electron withdrawing groups will be fluorine, chlorine, bromine, and iodine. And then we have CN, or a nitrile group, which generally, it's written as CN, but it can be written as this. So make sure you can recognize this. And we also have nitrile groups, NO2. NO2, if it's in a molecule, it will look like this, where your nitrogen has a positive charge. So that's very good, right? It's very electron withdrawing. Now, in terms of how these rank to each other, it really doesn't matter. What I wrote is the correct ranking, like in terms of increasing inductive effects. But out of everything, you should know this at least, like fluorine versus iodine, because they can easily give you this. They'll be like rank by anion stability, and they'll give you these two options. The first one has iodine, and the second one has like chlorine. What are you gonna do? They're both the exact same. Primary, they're primary, just primary, no allylic, but they're just primary, and the molecule is the exact same. The only difference is in the inductive effect. And you should know that chlorine, in this case, has a stronger pull than iodine. And if you wanted to have the best one, it would be fluorine. Fluorine is the best because it's electronegative. It's the most electronegative element. So it has the strongest pull, right? Whereas iodine has the weakest out of these four options. So this you should definitely know. Now you're probably wondering, I thought iodine holds a negative charge the best. Like if you're ranking anions, iodine actually is better than fluorine. And why is this? Because iodine has a large atomic radius, so it's able to disperse electron density across a wider radius, right? Whereas fluorine, it's small. I can't even draw these arrows properly because it's just so small. It's not able to spread the density across a large area. So as a result, iodine is very, very stable out of all the halogens. Fluorine is the worst. It's the least stable. But this is talking about holding a negative charge, right? If you're talking about holding a negative charge, sure, that's correct. But when it comes to inductive effects, your fluorine, it's not holding a negative charge, right? It's neutral. All that's doing is it's just pulling away electron density. So in that case, you do want the most electronegative one, or the one with the highest electron affinity, because it has the strongest pull of the electron density. So make sure you don't mix up the idea of inductive effects versus holding a negative charge, because those are essentially opposite here. I promise I'm gonna get to this part, like the primary, secondary, tertiary. I was just explaining electron withdrawing groups. Now for electron donating groups, very common ones are going to be, different hydrocarbons. So I just said CH3, but it could be a chain like this, right? Just a bunch of carbons and hydrogens. That's one option. You can also have NH2, or the H's can be anything, meaning any carbon. So you could have NH, carbon chain, or even N with two carbon chains, right? And the third one is OH, or O with the carbon chain, right? These are going to be your electron donating groups. Now when it comes to hydrogen, hydrogen is nothing. It's neither an electron donating group nor an electron withdrawing group. So the two things that we need to focus on are hydrogen and hydrocarbons. So look at this. For electron poor regions, so both carbocations and radicals, the more electron donation you have, the better, right? As we talked about. So tertiary, it's called tertiary because it has 3 carbons, otherwise known as 3 electron donating groups. Secondary is 2 EDGs, and 1 is 1 EDG, right? So the more electron donation, the better for carbocations. When it comes to these methyls, there's nothing. This one you can ignore because OH is an electron donating group, but just ignore that for now. They're not going to confuse you. I just drew it there as an example of what a methyl can look like. But look at this, right? I'm bonded to all hydrogens. This is 0 electron donating groups. So that's gonna be the worst. Okay. Now, when it comes to negative charges, it's the same thing but opposite, right? So we have 3 EDGs here versus, let's say a methyl. Let's draw this again. A methyl has 0 EDGs. Although this has nothing, it's better to have nothing than to have a lot of bad stuff, right? That's why our ranking looks like this. Okay, let's move on. I feel like I'm forgetting something, but I think it's okay. Bond dissociation energy is literally related to what we just talked about. Um, by the way, if you think I'm speaking for no reason, trust me, this is a type of ranking question that can show up. I don't even remember learning it in class, but they can ask you, right? They'll be like rank by bond dissociation energy, and they'll be like, 1 is highest and 5 is the least. Let's just draw some molecules, right? Honestly, let's do this right here. Okay, I'm just gonna draw 4 molecules. So 1 is the highest, 4 is the least. I'm so stupid. I didn't mean to draw the radicals. But that is what we're going to deal with. I kind of just gave it away. But this is what they'll do, right? They'll draw it out like this. So obviously we have more hydrogens like everywhere, but they only point out one specific hydrogen because they're asking about the bond dissociation energy of this specific C to H bond, right? Or whatever molecule you're looking at. So something you need to know, actually, I want to ask you first. If you remove a hydrogen, what's going to happen? A lot of you might think, oh, I'm removing an H plus, so I'm just going to have a negative charge, right? Normally that's the case. If you just extract a proton, yeah, you'll have a negative charge, but that is not the case here. When it comes to bond dissociation energy, it's referring to a homolytic cleavage. Homolytic is this thing that you guys recognize, or you should recognize, where it's like a single arrow, right? It's one single electron moving. So for your C to H, it's the same thing. One single electron moving to either end, giving you your radicals. BDE is very specifically referring to that. And it's important to know because if you ranked this by anion stability instead of radical stability, you're going to get a flipped answer because these are opposite in terms of their ranking and stability for the most part. So make sure you are aware. This is rank, forget BDE, rank by radical stability, essentially, okay? So what you can do here is just draw a radical in place of the hydrogen. So I'm going to cross this out. You got that. For the second one, it was over here. Third one over there. And fourth one over here. Now this one right here, what the hell is this? This is called vinylic. Vinylic is when you're right on a double bond. I didn't even add it to our ranking system because that's how bad it is, right? Let's just add it right now. Vinylic is trash. Just always remember this, right? You never want a charge. Doesn't matter what type of charge it is or radical, you do not want anything on a double bond. And the reason for this, it has something to do with the location of the orbitals in relation to each other, but also you can't resonate and there's just a lot going on. You just don't want this. This is horrible. So vinylic, okay, that's one option. This one is secondary allylic. Top right is just a regular secondary and bottom right is just a regular primary. So now, in terms of highest and lowest, right, high energy means low stability and low energy means high stability. So our most stable radical will be number 4, which is this one right here. Okay, then we got secondary, primary, and then the shitty vinylic. This is how you would rank this. Okay, let's move on. Monohalogenation. So monohalogenation, there's just two main types. They'll ask you, okay, what's the product of this? And then the product or products of this. Now, I think by now you all know that chlorination is not selective and bromination is selective. So if you did chlorination, you would get two products for this specific molecule. By the way, I think you should know this, but both of these are the exact same thing, so I'm only going to draw one of them. Right, guys? You do know this, right? Okay, bromination will give you this. Now, to be honest, if you know this, you're chilling. Like, that's the most you need to know for your test. But it is possible they might ask you to identify a graph or like explain the different features of the graph. So let's do that, and then I'm going to be a psychopath and explain everything in detail. So for monochlorination, your graph will look like this. And then for bromination, it will look like this. So this is exothermic, and this is endothermic because pretend this is higher than the other one, right? Okay, my fault. Let me just redraw this. Here. Br2 is endothermic. Now, this alone tells you if something is selective or not, right? I don't give a shit about the activation energy. Exothermic is not selective, and endothermic is selective. This relates to something called the Hammond's postulate. I don't think you need to know this, but it doesn't hurt to have extra information. But something you should know, right? Let's say we have our propane again. This position is the reactant, so it just is a propane, right? It's just a propane. Your product is what you expect it to be. Now, the intermediate is that relative minimum. Intermediates are going to be, your cations, anions, radicals, etc. So this will be your radical formation. Now, as far as what these two are, kind of have to go into a little more detail. But before we do that, I just want you to know, right, before I get into the stuff that you potentially don't need to know, keep in mind that if you're asked to decide which graph is which, know that the exothermic two-step one is chlorine and the endothermic two-step one is bromine. If for some reason they give you two endothermic ones and they ask about iodination, iodination should be endothermic but a higher activation energy. So this first step should be higher. Let's just put like 10, and this one will be like I don't know, 4 or something. Okay, iodination. A lot of you might know that if you were to monoiodinate something, it might not even occur. If it did occur, it would give you this. But some people say it doesn't even occur because it's so slow. It's so hard to reach the activation energy. There's better ways to do it. Okay. So now let's talk about what happens with monohalogenation in general. So keep in mind, right? Let's just do this. This is your Br2HV. Keep in mind, whenever you have a setup like this, whether it be your propane Br2 or something like this, you're not literally looking at one single propane or one single methylbenzene and one single Br2, one single KMNO4. That is not the case. They just write it out as one single one, but in reality, you have billions of everything in a solution. So I'm actually going to go ahead and draw this out, right? We have a billion of these propanes sitting there, and we also have a billion Br2s in the solution. This is important to understand like what's going to happen. This HV you might recognize as E equals HV or HF. This is light or energy, and that is also important because you're going to have a Br2 that's just together, and the light is going to cause that homolytic cleavage. So it's going to break up the single bond identically, right, to both sides, making your Br radicals. right? So I'm going to draw two Br radicals and get rid of this. Okay, so the first step, right? Keep in mind, just remember this in general. Forget OChem and stuff. This is like a biology thing. Radicals are very reactive. They're just going to try to react with everything. That's why, like, biologically, radical species are not good because they'll just react with whatever they can react with, especially the unwanted stuff. So your Br radical, it's going to approach this carbon and it's going to see that it has a hydrogen and it's just going to take it, right? So it's going to form a bond here, which means that the H is going to break its bond with the carbon. Okay, then what do we get? When this happens, you're going to get HBr, right? And you're also going to get a, propane radical. So what I'm going to do here is I'm going to highlight the bromine, this one, to show that we used it. Okay, and this is gone. The HBr is the same thing, right? This made the HBr. So now you're probably thinking, okay, I have a radical and a radical. Let me just straight up combine them, right? No, remember what I told you? I told you there's a billion of everything in the solution. So this bromine is actually going to come into contact with, like, another propane non-radical before it even sees this radical. And what that's going to do is going to do the exact same thing, right? It's going to take a hydrogen, it's going to form the bond here, and it's going to break the HC bond. What is this going to do? Form another radical. So now we use this one, right? And that's its own HBr. Okay, now what? We have two radicals, and we just have these Br2s everywhere. So what are they going to do? The Br2 will come into contact with a carbon radical, and as I told you, radicals just react with everything. So the radical is going to essentially form a bond with the bromine, right? And that means the bromine will break off from the other bromine. So what do we get here? Yet another radical, and now we have our first actual product, right? The 2-bromopropane. And as you can expect, right, another bromine radical will do the same thing here, and it's just going to be a continuous cycle, right? Just constant formation of radicals and formation of 2-bromopropane and HBr and all of that stuff. So that very first step, the very first time you form a radical, is called initiation, but then that chain reaction we just talked about right now is called propagation. Then eventually everything will be reacted with, and all you're going to be left with is 2 bromine radicals from different Br2s. There's nothing left to react with. So to finish everything, they're going to connect to each other and form another Br2. And that is called termination. Okay? So here's the thing. I told you that you don't really have to know all of this, but there is a key thing I want you to recognize. And it goes along with, like, why bromine just forms over here. Take a look at this, right? It doesn't matter which graph you're looking at, but this right here, or let's just circle this actually, this right here is your rate determining step. It's a 2-step reaction, but the first step has a higher activation energy, so the rate is solely determined by the formation of this, which is your intermediate. And that means if you go with endothermic, right, the stability of your intermediate will determine your final product. So, for this propane, you have two options. You can either form a secondary or primary. Secondary is more stable, so it's more favorable if you form the more stable one. And if you form the more favorable one as a radical, that means your bromine will attach in that more favorable position. That's why all of this occurs. When it comes to chlorination, the formation of the radical, it is the rate determining step, but because it's, like, closer in energy to the reactant and not the product, it doesn't really matter, like, which one you get. Chlorination will still have a major product, like this will be more favored, but both options will be made. So just keep that in mind, right? Just forget everything I said, right? The biggest thing I want you to remember is this right here is your radical intermediate, and this is the rate determining step. Okay, that's what I really want you to take away from this. And just to complete the graph, let's just complete this real quick. We kind of already talked about it, but the first transition state is when your bromine radical is taking the hydrogen and breaking off the bond with the carbon. The second transition state will be when you have your radical and you have a Br2 trying to form a bond here, and this is breaking off, right? That would be your second transition state. So make sure you understand this and you're chilling. Now, let me show you like how they can ask bromination, chlorination in a manner that's a little bit more difficult. Like I think it's pretty obvious at this point, like chlorination or bromination, especially for something like this. But there's two things, right? They can just be like the typical, we just did it, but I'll make it a little bit more complex. They'll be like, you know, draw all the products for Cl2HV and all the products for Br2HV. For Cl, it's going to be everywhere that's not a double bond. So you can form it here, here, and here. Keep in mind, this and this are the same thing, so I only marked one of them. That's three options. Bromine will go over here because tertiary benzylic, that's your best one. Okay, that's cool, right? Another way they can ask the question is like this. They'll be like, okay, I'm bonded to C4H9, and C4H9 has many isomers, right? The A isomer will give me like, I don't know, 3 products. The B isomer will give me 1 product, and the C isomer will give me 4 products. And they'll ask you, okay, what is C4H9 isomer A? What is isomer B? What is isomer C? So how do you do this? Let's draw them out. Let's draw the different isomers. The easiest way to do this is a single chain, right? So we can go like this. Make sure everything adds up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's just going to be a straight chain. And how many places can we add chlorines to make oh my god, I said it, to make unique products? There is no symmetry here because it's part of this, right? So each location will make a completely different molecule. So that's 4 options. This in particular would be isomer C. Okay, let's continue this. Just branch it out, right? Instead of drawing a 4 carbon straight chain, draw 3. So you have 3 here, and add a add a carbon somewhere, like branch it out. Like let's just branch it over here. Okay, how many places can we add? We can add it here, we can add it here, and we can add it on either end. They're gonna equal the same thing. So this will give us 3, right? This would be option A. Now, if you're wondering how I determine symmetry, this is what I like to do. So just follow along, right? So we have our benzene thing, and then we're going out like this. We're going like this. Okay, now at this point, I can either go 1 carbon over here or 1 carbon over here, right? It doesn't matter. They're both CH3s, and I can go either direction. So they're identical. So it doesn't matter if I add a chlorine here or a chlorine there. It's the exact same thing, right? I'll give you another example. Let's draw another isomer. This is another isomer. What do we do here? Okay, first of all, let's determine how many unique carbons. This is a unique carbon, but it already has maximum bonds, so you can't add a chlorine there. You can add it on the ends though, right? You can add it on these, but there's only 1 product because these also happen to be the same thing. How do we know this? All right, follow again. You have your benzene, you go here, and now at this carbon, I can either go 1 carbon up here, 1 over here, 1 over here. They're all the same thing, right? It doesn't matter which direction I go, it's the same thing. So within this, I have symmetry. So that's kind of how you look at this. So this would be the isomer B, because there's only 1, unique monochlorinated product I can get. Now, one more thing before we move on, I want to mention NBS. I think you might have seen this before. NBS is essentially bromination, but for when you have double bonds present. NBS, the B stands for bromo. It's called N-bromo-succinimide, don't worry. But the B stands for bromo. So let me show you something, right? If you had this, if you do Br2HV, actually this is a horrible example. Let me just add some carbons 1 second. Here, okay? If you do Br2HV, you'll get this right here. What happens if you do NBS? Look at that. I got the exact same thing. So what is NBS? NBS, all it is a more efficient way to monobrominate when you have a double bond present, right? You can use BR2. I don't think they'll give a shit on your exam. You can use BR2 or NBS. It's just I'm bringing this up because I want you to recognize what NBS is in case they throw it at you and you don't know what it is. But we have both options because technically in the real world, when you're in a lab, NBS is a better way to add in a double bond, add a bromine when you have a double bond present. I think when you try to do BR2 and you have a double bond present, it kind of like loses its selectivity. So like we expect it to be here, but I think the BR2 ends up going other places because it just wows out when there's a double bond. But it doesn't matter, right? They're not going to care on your exam. So you can use either. Just be able to recognize NBS and you're good. Okay, that is it for monohalogenation. Let's move on to alkenes. Okay, what is this called? It's called an alkane with an A. As soon as you add a double bond, now it's called an alkene with an E. That's all it is. When it comes to naming, follow your typical IUPAC rules. Your double bond has some value, has some priority, so you're going to number your carbon chain to have your double bond on the lowest possible carbon numbers. So this is a pentane, right? Or it's a pentene, but it's 5 carbons. So you're going to number it this way: 1, 2, 3, 4, 5. Okay, so it's going to be a pentene. Okay, cool. But what about this? This is also a pentene. So how do we distinguish them? You look at where your double bond is. So it's on the 2 and 3 carbon. You just take the lowest of the two, and it's understood that the bond is between the 2 and the 1 in front of it, the 3 carbon. So you can call this a 2-pentene. For this one, you can call it a 1-pentene. And once again, it's understood when you say 1-pentene that the double bond is between 1 and 2. And for 2-pentene, it's 2 and 3. Now, this is the original method of naming it, but the newer way, and something you should still recognize, is that you can call it like this: pent-2-ene. And over here, pent-1-ene. It might seem silly why we do this, but, I'll just give you a little glimpse of how it can be helpful. Okay, for example, this molecule right here, the name of it would be prop-2-ene-1-ol. If I did like 2-propan, I don't know how to even name this the other way, like 2-propanol-1 or something. I don't know, bruh. That's horrible. But like, you see how it would get chaotic? Like if I do like 1-propanol, 1,2-propan, like it just makes no sense. I don't even know the original method, I'm not gonna lie. This is so easy. You can clearly tell, okay, the ene is on the 2 carbon, the alcohol is on the 1 carbon. So that's why they do this. That's why they break the words up and include the number in the middle. That's why. But you're not gonna deal with this right now. So like, it doesn't matter if you want to call it 2-pentene, which is cleaner. In my opinion, you can do that. Doesn't matter. But just recognize both of them. Okay. Now, what about this? What if you had... How would you name this? Simple, right? Just number it like usual. So it's going to be a hept something. Okay, you might know. Okay, 1, 3, hept. This would be called heptadiene. Don't forget the di, because there's 2 of them. Or if you want, you can call it hept 1,3-diene, same thing. And then if you had a third, it would be 1, 3, 5 heptatriene. So it's just the usual, right? You know, you should remember this type of thing from your IUPACs from before. The same thing follows. Okay, cool. Let's get rid of this. Now I have something else that I want to ask. Both of these are 2 butenes, but they are not the same thing. They are not the exact same thing. If you had this, these are the same thing because you can just rotate single bonds, but you cannot rotate double bonds. So I cannot just rotate this and get this, right? That is not going to work. So these end up being completely different molecules. They're isomers of each other. They're diastereomers or geometric isomers. Geometric isomers, but they're not the same thing. So you might recognize the noob method is calling this trans and this one cis. And I mean, that's perfectly fine, right? You can call this trans 2-butene and the other one cis 2-butene. But the expert method is using E and Z classifications. So take a quick guess. Which one do you think is E? Which one do you think is Z? Okay, you're wrong. Trans is going to be E. And cis is going to be Z. Now, I know you're wondering, bro, how do you remember this? I got you, bro. Thanks for asking. Cis is on the same side. So as you can see, both carbons are on the same side, which is cis. Cis just means the same. Trans means the opposite. So E is the only leftover one, so that's what trans refers to. So if you want to be an expert organic chemist, you can call this E2-butene, and the other one you can call it Z2-butene. Okay, let's add in one more thing. This is not going to have an EZ naming. This will just be called geminal. The only instance you'll ever have this is if you have an alkene where only one carbon has substituents. This is the only time you'll see it, so just keep that in mind. I'm going to refer to it again in a couple minutes, but just recognize this. So let's talk about alkene stability. Okay, so the first thing you want to look at is number of substituents. More is better. More is better. That's the first thing I want to look at. So if I'm looking at this versus this versus that versus this, right off the bat, this is the best one. This is second, third, and fourth. So when I'm talking about substituents, I mean substituents on the alkene carbons. So this first one, right, I have 1, 2, 3, 4. This is called tetra-substituted. This one is tri-substituted. This one is di-substituted. And this one is mono-substituted. So the more substituents you have, the better. And the reason for this is something called hyperconjugation. I'm not going to go into detail. I don't want to confuse anyone. So in case you're wondering, hyperconjugation has something to do with the stability of your alkenes. But the more substituents you have, the better. That's the rule of thumb. Let me get rid of this. So obviously it's not going to be that simple. They're not just going to give you 4, 3, 2, 1 and be like, what's the most stable? They can do something like this. Okay, which of these is more stable? Or let me add one more actually. Okay, rank these in terms of stability. So we see that both of these are tetra substituted and this is tri substituted. So I already know that the third one is my least stable just because of the number of substituents. Now between these, how do I decide? Okay, you want to determine cis and trans. So what you do is think about the priority you use for stereochem. So you want to use the exact same thing. I want to look at my directly connected elements and determine what's larger for each carbon. So for this carbon, we're both bonded to carbons here. Let me do a different color. Both of them are bonded to carbon. Okay, so we take it a step further. This carbon is bonded to another one, whereas this one is bonded to nothing. So the bottom one takes priority, right? So I'm gonna put like a little X over here. Now for the left one, which one is larger? Bromine is larger, so I'll put an X over here. Since your two substituents, your two highest priority substituents are on opposite sides, this will be trans. And then over here, it will be cis, because they're on the same side, so cis. So, which is more stable? Just remember, trans is better than cis. And I'll mention one more thing. Trans is better than geminal, which is better than cis. But this only applies to di-substituted because geminal, like, by definition, you have to only have two substituents and it has to be on the same carbon. As soon as you add another substituent, it's going to be tri-substituted and you get cis and trans, right? So it's not, you can't have geminal. Now this right here is another instance of difference of opinion. I think there's a professor that says geminal is better than trans. I don't really remember, but if you have Dr. Pan, you're good. Unless I'm tripping, but this should be the case. So yeah. So let's do some more what's it called? Like let's do some more like cis trans determination, and I'll give you one more ranking at the end, I think. So determine this one. Let's do this. And just tell me, cis or trans. So for this first one, you might realize, okay, I'm so sorry, I didn't draw the double bond. So you might realize, right, the left one, the largest substituent on the left carbon is down here, but on the right one, they're the exact same thing. So you can't say one has priority over the other, they're the exact same. So something like this will not have a stereoisomer. This thing cannot be cis or trans, so it's nothing. And it's fine because even if you drew it like this, it's the exact same thing. Because you can't rotate the double bond, but you can just rotate the entire molecule. But you can just twist it, right? You can just turn it around. Like, I mean the entire molecule, right? Not the double bond. So it's the same thing. You can't say one is better than the other. They're the same thing. Okay. What about this one right here? On the right carbon, just look at what you're directly connected to. Yes, this is larger than NH2, but it doesn't matter. Carbon versus nitrogen. Nitrogen is better. It's larger than carbon. So this is our largest priority. What about the left side? This is larger, right? It has a lot of fluorines, but remember, just look at what you're directly connected to. I'm directly connected to a fluorine versus a carbon. Fluorine is bigger, so this is our, priorities for each carbon. So this is opposite sides. This will be E or trans. So that's how you deal with this. Now let's do one more and then we'll be done. I'll just make it really simple just to get the point across, right? Okay, very easy. This is tetra, tri, di, trans, digeminal, and then mono. one more thing to remember is that these are diastereomers. These are diastereomers of each other. But once you do this, this is not a diastereomer. Okay, this is constitutional isomer. Just think about it. Over here, each carbon is bonded to one CH3. Right? Even over here, I'm bonded to CH3. But what happened over here? This carbon is now no longer having any CH3s. It's just H's. But this carbon has two CH3s. So by definition, that's a constitutional isomer. That's why like geminal is its own category, to be honest. But cis and trans, like true cis and trans, are geometric or, diastereomers. Okay, let's move on. Heat of hydrogenation goes along with alkene stability. So, what they'll do is they'll be like ranked by heat of hydrogenation. Rank 1 will be the lowest. I think it looks like this. I forgot. Something like that. It will be your lowest, and they'll put in parentheses lowest negative value. And then, I don't know, 5 will be your highest heat of hydrogenation, which means your largest negative value. And so what I mean by this is negative 10 versus negative 90. Negative 10 is a lower heat of hydrogenation. I know negative 10 is larger than negative 90, but you're looking at the absolute value, so 10 is smaller than 90. Now, what else you should know is that lowest heat of hydrogenation equals more stable, and the higher heat of hydrogenation is less stable. So literally what we did right here, this ranking, they could just ask, rank it by heat of hydrogenation, and your ranking would be the exact same here, just because the stability is related to lower heat of hydrogenation. So definitely be familiar with this concept because they can easily ask this in your rankings. Okay, now the fun stuff, as if the other ones were not fun. Nucleophiles, electrophiles, and leaving groups. A nucleophile is nucleus loving, in other words, positive charge loving, which means that a good nucleophile has a negative charge. Because if you have a negative charge, in order to neutralize yourself, you need something positive. So they're attracted to positive stuff. Electrophiles are the opposite. They're negative charge loving, and it can have a positive charge, or even partial positive. This one can be partial negative, right? But the point is that electrophiles are electron loving. They're negative loving, and they're going to be partial positive because same reason for nucleophiles, right? Which means that nucleophiles are attracted to each other, right? They're attracted to each other because both have something that the other doesn't, okay? Now, when it comes to nucleophilicity, let's draw a periodic table. Remember this mnemonic forever, okay? Bean. B stands for basicity. This is actually going to be important for elimination. So actually, I'm going to circle this. It's a good one to know. E is just electronegativity. This one you should know. A is acidity. And then N is nucleophilicity. So I'm going to circle this one too, right? If you know these two trends, you're chilling for some of these ranking questions. So B is up to the left, and nucleophilicity is down to the left. That's your ranking. So what does this mean? If I'm asked to rank by nucleophilicity, I'm given these. Your greatest nucleophile here will be pH2. And then it will be nitrogen. then sulfur, then oxygen. So when we draw a periodic table, we have this one also has a difference in opinion, like between nitrogen and sulfur. I've heard different things, so I'm actually gonna, let's just scrap this for now. Forget the sulfur part. We'll keep it like this. I don't want to tell you the wrong thing. But as you can see, right, if you go down to the left, phosphorus is bigger, and it's furthest to the left, so that's why it's number one. Then we have nitrogen, and then oxygen is highest and it's the rightmost, right? So that's how you have your ranking like this. Now, that's if they're all neutral. Let's do another example. I'm actually going to keep these here. I'm going to add a couple other things. Okay. What you need to know is if you have an Na, an Li, or a K, these are all what's known as counter ions. So if you look at this, it's literally S minus with an Na plus. The Na plus or the K or the Li is just there to neutralize your sulfur in the solution. But in reality, it easily dissociates, and the sulfur will be a negatively charged sulfur. So if you ever see anything like that, like if you see OLi or even this ONa, you're actually looking at a negative charge on your nucleophilic atom. So very, very important to know. Because if you have a negative charge, that's like a really good feature of a nucleophile, right? If you look at NH2, this is neutral. There is no negative charge. Or if you look at OH, do not think that this is this right here. This is not the case because the OH bond is covalent, right? There's two nonmetals. So they don't just dissociate, they're harder to break apart. But when it comes to a metal and a nonmetal, like sulfur and sodium, they're ionically bonded, so they can easily dissociate. That's why you can say this. So let's do our ranking again. The first thing I want to look at is charge. Then I can look at the actual trend. So our strongest nucleophile, it's going to be either of these, and sulfur is larger than oxygen, so this will be rank 1, this will be rank 2, and now for NH2, pH, and OH, those are their own category. They're all neutral. So we're going to do the trend again for those three. P is the furthest to the left, and this is the lowest, so this will be number 3. Nitrogen is 4, and O is 5. So do you see how oxygen ended up being rank 2 and also the worst rank? That's because in rank 2 it had a negative charge, and in rank 5 it didn't. So oxygen is pretty trash. It really sucks. But if you have a negative charge on it, it can be good. So keep that in mind for sure. Okay, now let's talk about leaving groups, or also leaving groups and electrophiles can be the same thing, right? So electrophiles have leaving groups. So if you have this is an electrophile, but when we say electrophile, we're very specifically talking about the certain atom that's electrophilic. So as a whole, this thing is an electrophile, but the actual electrophilic atom is this one right here. It's partial positive, and your bromine is partial negative. So an electrophile should have a leaving group. That's like how you can identify them. And a leaving group is just something that leaves. So if your bromine leaves, it will be by itself, and it will look like this. Br minus, and as you should know, it's very stable as an anion, so it's a good leaving group. But let's look at an example of a bad electrophile. Fluorine is not going to leave because we know this. F minus is trash. This is bad. So keep this in mind. what they can do is ask you like which one reacts the fastest in, I don't know, just any substitution reaction. They'll give you these options right here. Iodine would be the best because I minus is the most stable. Br would be second because Br is pretty good. It's just not as good as iodine. And then the fluorine one would be 3 because fluorine won't even leave. Like it literally won't even react. But if it did, somehow, it would be very, very bad. Like it would take a lot of energy to remove that fluorine. So that's something to keep in mind. Now, for leaving groups, right, we talked about the common ones, right? Your leaving groups are only going to be chlorine, bromine, and iodine, but there's another category, it's the oxygen ones. So I want you to remember this. OH sucks, right? If we're saying that fluorine minus is bad, what makes you think OH is any better? This shit's trash. It's really bad. Like, you don't want this. Look at the periodic table. It's right next to fluorine. So, you know, they're essentially the same thing. You don't want this. But you can make OH a good leaving group. There's two main ways to do this. One is to protonate, and option 2 is to resonance stabilize. So for protonation, you know, you can have this, and you know, you can literally just write H plus, or you can write a strong acid. So we'll do like H3O plus or HCl. If you do this, okay, wait 1 second. Really quick disclaimer: try not to use H2SO4. I'll explain later on. Try not to use it, and also just try not to use an acid. You know what? I can't really explain this right now until we get to that part. So I'm gonna just say use this or this. Don't use your strong acids right now. Anyways, what this will do is protonate your oxygen. So now you have OH2 plus. What happens if this leaves? It's H2O. It's water. It's neutral. There's no charge or anything to worry about. It's really good. So that is something you can do to make OH a good leaving group, protonation. Now option 2, resonance stabilization. Okay, I'm going to bring this down here just so I can have some space. Resonance stabilization, what does this mean? The most common method that you learned about in class is tosylation. So you've probably seen this. Tosyl chloride, TSPMO, right? In short, what this does is it will give you this, OTS. And OTS is a good leaving group. I'll explain why, don't worry, but that's like what you've learned. So that is one thing. I'm actually going to talk about this before I get into the next ones. What is a tosyl? Tosyl looks like this. This is tosyl chloride. I'm going to be a nerd and explain why it's called tosyl chloride. This, a benzene with a methyl, is called a toluene, and this is called a sulfonyl group, or you can say a sulfonyl chloride. So toluene, sulfonyl chloride, if you just make it short, you know, you get the TO, the S, the Y, and the L, you get tosyl chloride. Okay, that's why it's called that. So TSCl is this thing that I just showed you. And what happens when you react it with an OH? Essentially, what happens is your oxygen is going to attack the sulfur, and okay, something else happens, but just to keep it simple, the chlorine leaves. The chlorine's like a leaving group, right? So then what do you have? You have this. pH is your benzene, okay? So you have that, and you also have an H, and you have a Cl minus. So what do you see right here? You have a plus and a minus. In order to neutralize it, the chlorine will just take a hydrogen and break the bond. So then you end up with this, right? here. Once again, P equals benzene, pH. You have this, and then you HCl, nobody cares, it's gone. So then if you kick this off, what do you get? Look at this. You have resonance with both of these, right? You can either do that or you can do this. That's very good, very stabilized. You should definitely know that negative charges, resonance, stabilizing it, doesn't matter if it's negative or positive, but resonance is always good. So it's now fine leaving as a negative charge, right? This was bad, but this is amazing. So that is what tosylation is all about. Something that I don't think they cover here, but it's good for the MCAT, is called methylation. So if you know what tosylation is now, you can take a guess on what methyl stands for. It's literally the same thing, but it's methyl, right? Methyl sulfonyl chloride. You just take the Me, the S, the YL, you get methyl. It's the exact same thing, right? It doesn't matter. You have a benzene with a methyl or just a methyl. The resonance happens here, right? The resonance happens here with these oxygens. So that's why that's another really good option. And a third and fourth method will involve PBr3 and SOCl2. So I don't really feel like getting into the whole what it looks like. I'll do it if you guys want, but PBr3 looks like this. Something like that. I don't know. I think there's like double bonds or something. I don't know. It looks like this. SOCl2 will look like, I don't know, bro. I look, you forgot, but it's something like this. Just keep in mind that whatever we showed for methylation and tosylation, where there's like a whole mechanism, like you're attacking something, all that, the same thing will occur for both of these. But what you want to know is that if you react an OH with a PBr3, you're going to stabilize it, but your ultimate product will be this, right? Because within this whole like mechanism, your O is going to essentially replace one of these bromines. So it will become like this, right? And then your bromine will be on its own, and it's going to take place of the, the leaving group. So it will attach itself. Whereas for this right here, if you do SOCl2, same thing, right? The oxygen will get stabilized by this thing. It's going to steal one of the chlorines, and the chlorine will instead attach itself on the carbon. So just something to keep in mind. If you're tosylating, all you're doing is forming a good leaving group, and then you can react with whatever. But if you're doing PBr3, you're going to get a bromine on your carbon. If you're doing SOCl2, you're going to get a chlorine in place of it. Now, don't worry, because you can still replace these, right? Chlorine and bromine are leaving groups themselves, so you can do that. Like, you can use them as their own leaving groups, but it's a little bit nuanced. I'm going to explain this towards the end, unless I forget what I mean. But just keep that in mind, right? You have many options here. Definitely don't be like scared if you see PBr3 or SOCl2, because I explained it to you, right? I don't know if they talk about this in class, but it can show up on your exam. And by the way, if I said anything vague, I kind of did it because I didn't want to use the terms SN1 and SN2 just yet, because we didn't talk about it yet. So when I talk about it, I can explain a little bit more. Okay, let's move on. So now we have a good idea of what nucleophiles, electrophiles, and leaving groups are all about. Let's put it together into actual reactions. So SN1 is substitution, and 1 refers to the reaction order. So reaction order is 1. Definitely, oh my god, please know this, okay? The rate is K times substrate. That's it, okay? It has a reaction order of 1 because the substrate is the only thing that affects the rate. K is a rate constant, nobody cares. But the substrate, very important. As a result, it ends up being a 2-step reaction. So if you look at the reaction diagram, it's gonna look like this. It's exothermic, and the first step is rate determining because the activation energy is larger than the second step. So that makes a lot of sense because the first step is what you all should know as the carbocation formation. The second step is the nucleophile coming in, right? So let me explain this a little further. That was just an introduction in case you already know what the hell is going on. But what does it look like? Let's do this. Let's say you have this electrophile with CH3OH, nucleophile. The very first step, right? Step 1 is your leaving group will leave. So my Br will leave, right? So I'll have Br minus just floating around. And as a result, I have a carbocation. This is that step 1 we're talking about, right? So this intermediate is your carbocation. And as we talked about in monohalogenation, your rate determining step is going to be an intermediate, right? And it's going to determine the final product. So, and it's also going to determine the speed of the reaction because you only go as fast as your slowest step. So this is the slowest step. It has the highest activation energy, but that's all we care about. That's why the rate is K times substrate. Because the nucleophile, we didn't even talk about the nucleophile yet. We just said it's there. We didn't talk about it. I don't really care if it's CH3OH or CH3PH2. It's not going to make a difference to the speed of the reaction because the speed is solely determined by the formation of this. So if you're talking about like, oh, let's rank which one reacts faster, like, these two. I'm going to react the first one with CH3PH2, the second one with CH3O minus. Sorry, let's do OH. And let's say these are both SN1 reactions. I don't give a shit about the nucleophile. Like, forget that. That is not going to make a difference. What I will look at is the substrate. I form a carbocation on the tertiary position for the first one, and for the second one, secondary. Which one is more stable? Tertiary is more stable. So as a result, I know this reaction will occur faster because, once again, your rate is determined by the substrate. The more stable your intermediate is, the faster it can be achieved and the faster your overall reaction occurs. Definitely very, very, very important to know. Okay, so this was step 1. Then step 2 is your USMLE exam. Sorry, guys. Okay, step 2 will be your nucleophile coming in. So usually it's going to be neutral nucleophile, which makes it weak. But it's going to use a lone pair to just attach itself to that, electron poor carbon. So you'll get this. You'll get OCH3, and technically you have an H, but just keep in mind, they're going to tell you, it's just like a known thing. You're going to have something called an acidic or a basic workup step. And all that does is it just neutralizes any unnecessary charges. So you don't even have to go into detail onto what actually happens. You can just say, oh, this is my product, OCH3, right? That's what you need to know. Sometimes we write it like this, a minus H plus. That just means this H is leaving and your O will be neutral. So that's what happens. So SN1, let's put it together. SN1 is good when you have, let's write once steric hindrance. Or you can think of it as more substituents. You also, okay, look, you don't need a stronger weak nucleophile, but you can say generally has a weak nucleophile. But remember, doesn't affect your rate. It just happens that your weak nucleophiles end up doing SN1 because strong ones generally do the other mechanism, which is SN2. Okay, that's it for SN1. We also have like potential to do carbocation rearrangements, which we didn't even talk about yet. And the last thing, forms racemic mixtures, which if we don't talk about SN2 yet, I can't explain it, but I'll mention it and explain again when I get to the SN2 portion of this. But, you know, the best way to know if something's SN2 is just seeing both things that you have, right? If you have a tertiary, this has to be SN1. And once again, I can't really explain why until we talk about SN2, but this, and then, you know, weak nucleophile, just anything neutral. So like CH3OH is a very common one. You also have CH3SH or NH2, right? These are all neutral. The moment you have this right here, it's a little bit ambiguous. It could be SN1, it could be SN2, just depends. If you had a strong nucleophile with a tertiary, it would be SN1 for reasons I can't mention once again. But, you know, just like a mix of these things you have to look at. Okay, let's talk about carbocation rearrangements. So there's 3 types of rearrangements. The first 2 are easy. So the first one is a hydrogen or a hydride shift. So let's say we have this right here. Your bromine leaves, it will form a carbocation on this secondary carbon. And let me just draw in a hydrogen right here. We have one hydrogen. This also has a hydrogen. The hydrogen, the purple one, is smart. It's going to be like, okay, let me just move over. So this will come over here. So what you end up having is both blue and purple hydrogen on this. What about this? Now it's missing a bond. So your carbocation ends up being over here. Now why does this occur? Look, this was secondary and now it's tertiary. As I mentioned before, rate determining step, you want it to be the most stable intermediate. So if you can make yourself better than what you're originally as, that's good. So tertiary is better than secondary. So this will occur. Now let's do another one that's pretty similar. It's called a methyl shift. So if you had this, okay, first step, bromine leaves, you form your carbocation. It's the same thing except it's a methyl now, right? So one of your methyls is going to be like, okay, let me just move over here, and you're going to get a molecule that looks like this. This is lacking a bond, so your carbocation will be here. Same thing, it was secondary originally, now it's tertiary, so it's better. Now keep in mind, if you can technically do both, you know, you're just gonna do like the easier one. So if you had this, you might think like, okay, what if I move, what if I just move the methyl here, and then I move one of my hydrogens over there? Okay, that will give me this. That's like OD, don't do that shit, because that's like 2 whole movements, and it's unnecessary. If you had the choice, right, methyl or hydrogen, just do the easier one. Let me give another example. So I'm over here. I can either move there and the methyl comes down, or I can move over here and the H comes down. I don't think it's that deep, but I would go with the H shift. Like I would just move over here, because moving a hydrogen is way easier than moving a methyl. It requires less energy. So the thermodynamically favorable one would be over here. And in both cases, you get a tertiary. So like, you know, just make it easy on yourselves, right? And make it easy on these damn carbons. So that's what you can do. Okay, so those are pretty simple. Now let's do the annoying one, which is not annoying for me. It's very fun. But this is called ring expansion. So I want to mention one thing. Triangles and squares suck. These are very strained. It's called ring strain. The triangle is not going to apply here, but just know for the future, triangle cyclopropanes are trash. They're very, very like, oh my God, look at the angles, man. This is, I don't even know, 60 degrees. What is the bond supposed to be? Like 109.5? I don't know. That's bad. So that's bad. Squares are also bad. They have like shitty angles. Pentagons, on the other hand, are good. Pentagons, hexagons, those are good. But what I'm trying to say here is that if you have a square, like literally 99.9, fuck that, 100% of the time, you're going to have the ring expansion. You can also do a ring expansion with your cyclopentanes, but you don't have to. But what I'm trying to say here is that if you do a ring expansion, it's going to be either the pentagon or the square. The square, 100%. The pentagon, it just depends on the context. I'll explain what I mean. So, what is ring expansion? Ring expansion happens for two reasons. In the case of a cyclobutane, it's there to both offer a more stable carbocation, moving from a secondary to a tertiary, but also just relieving that ring strain. For a cyclopentane, it's not there to relieve ring strain. If it happens, it's only there just to move from like a secondary to a tertiary. So just something to make it better. So what does this look like? Let's say we have a carbocation here. Okay, you might think, oh, let's just do an H shift and move it over there, so I'm gonna get this. This in particular, do not do it, because I told you we're trying to get rid of this, right? Yes, my carbocation has three substituents, whatever, tri-substituted or tertiary, but this whole thing is not stable because we have this cyclobutane, which is ring strained. So what we're going to do is essentially we're going to break this bond and reform a bond between these two. So I'm going to number these carbons, right? We have 1, 2, 3, 4, and 5. So what happens? Let's draw our cyclopentane and just number it 1, 2, 3, 4, and 5. Right? We formed a bond between 4 and 5. But initially, carbon 5 only had 3 bonds, right? It only had 2 hydrogens and a bond, right? So look at this. 2 hydrogens and 2 bonds. That's perfectly fine. There is no need for a carbocation there. What about number 4? Number 4 had 2 hydrogens and it had 2 bonds. Okay, sure, we broke this one, but we still formed another one, so it's the same, right? So carbon 4 is fine. But what about carbon 1? Initially, it had 1 bond, 2 bond, 3 bond, and 4 bonds. But what happened here? We're breaking this bond, so now carbon 1, it only has 3 bonds. So what that means is you're going to have a carbocation on the 1 carbon. Now, I know this is like it's just a basic cyclopentane, like you can put the carbocation anywhere, but I did this little exercise to show you how to actually understand where everything went and where the carbocation moved, because when you have substituents, it will be confusing. So this is good, right? You had 2 options. Option 1 was to form a cyclobutane or keep it like that and have a tertiary. But tertiary in this case is not good because of the ring strain. Cyclopentane is chillin', right? Yes, this is secondary. It's not as good as tertiary, but because you have a cyclopentane, it's normal now. So this needs to happen, right? That's why I said if you have a cyclobutane 100% of the time, you're going to have a ring expansion. Now let me show you something else. Let's do the exact same thing, but for cyclopentane. If you had this, remember what I told you? Cyclopentanes are fine. So you can literally just move that carbocation down here and you're good. In fact, I think this is better because if you made the cyclohexane, you're gonna have a secondary, and as I told you, pentane's already like it's already stable, so making a cyclohexane is not gonna do anything in terms of stability. So like it's unnecessary. So this is fine. Okay. But if you're wondering, okay, when the hell will it show up? Let's do another example. Let's just do this. So for this one, let me see what else I can do. It's hard to think of things on the spot. I don't know, we'll do something like that. Yeah, I think this is fine. So, you might be thinking about methyl shifts. I don't know if this is a good example. I low-key forgot. I don't know if you can do a methyl shift here, but what you want to end up doing is a ring expansion because you want to make this from primary to tertiary. And so what you can end up doing is, let's just number this 1, 2, 3, 4, 5, and 6. Notice how I didn't number the other substituents because I don't really care. So look what I'm doing. I'm breaking a bond between carbon 5 and 4, and I'm forming it between 4 and 6. So I'm going to draw my cyclopentane. And I'm going to number it 1, 2, 3, 4, 5, and 6. So carbon 1 has a bond, or like a metal. Carbon 5 also has a metal. And, sorry, let's redraw this. So 1, 2, 3, 4 formed a bond with 6, so it's going to look like that, right? So carbon 5 has a metal, carbon 1 has a metal, carbon 4 and 6 formed the bond, but carbon 5 is where the bond broke, so carbon 5 is going to have our carbocation now, and this is tertiary, so that's like another instance where like you can actually have a ring expansion. Once again, for this specific question, as far as if you can do a methyl shift or not, I think you can, but like usually when they give you a question like this, it's either going to be a regular hydrogen shift or a ring expansion. And keep in mind, ring expansion will only be if you have a ring to begin with. So if your entire test has no rings and then they automatically like randomly throw one at you, it's probably going to be a ring expansion just because they want to see if you know how to do it. And one more time, it's my 5th time saying this, if you have a cyclobutane, it's going to be a ring expansion. One more thing to mention before I move on is that carbocation rearrangements can only happen if you're one away from something. So if you're thinking like, oh, I can rearrange this into that is not going to occur because we're too far away from each other. If it was like this, on the other hand, then sure, I can move one away and get this right here. So this is important to know because if they give you this and they want you to react with methanol, the first step is forming your carbocation. So you'll have this, and as we know now, it's going to do a shift and form that, and then your O will attach there. So your ultimate product will be this, right? So we didn't directly just replace the bromine, we moved things around. That's why it's good to know this will be your product. One more thing that we talked about before, like the racemic mixtures. Racemic, what this means is, let's say they give you this. And then bromine, and let's just say it is an SN1 reaction and they do methanol. You're going to get a mixture of both. One second. Honestly, this was a bad example. Let me erase some of this stuff. Let me move. Okay, let's say you had this. You react it with methanol. And I'm telling you specifically to do the SN1 reaction. You're going to get a mix of this and this in equal amounts, otherwise known as a racemic mixture. And why is this? It's just because the bromine leaves, right? This is planar. There is no like chirality here. So your methanol can attach from either side. Like it doesn't matter. So you're gonna get both of these. And if you have 50% of each enantiomer, it's called a racemic mixture. So that's something to keep in mind. One more thing I completely forgot to mention is SN1 prefers polar protic solvents. I'm just gonna leave this at that, but I'm gonna mention it after we talk about SN2. So just remember this, okay? So polar protic carbocation forms as rate determining step. You also have generally weak nucleophiles and likes, I'm sorry for my shitty handwriting, like steric hindrance. That's pretty much it for SN1. Okay, now SN2 should be a little bit easier. SN2 is hates sterics for both the nucleophile and the electrophile. Prefers a strong nucleophile, and it prefers polar aprotic solvents. So for this one, it's polar protic. For SN2, it's polar aprotic. Keep in mind, you can use polar protic in SN2, and you can use polar aprotic in SN1. It's just in terms of favorability, it's better to have it as we described. So SN2 is a one-step reaction, and please, for the love of Allah, please remember this, okay? Rate is K times substrate times nucleophile. This is why it's called SN2, because the reaction order is 2. We have two things going on, right? So this time, your nucleophilicity does matter. It does affect the rate. And your reaction is a one-step reaction. It's also exothermic, but it's a one-step reaction. So there is no intermediate. You just have a transition state. That's all you have. Reactant, transition state, and product. That's all you have here. So let's talk about some examples. Oh, one more thing is you're going to invert your stereochemistry. In other words, it's stereospecific. So let's say you have this. Let's do iodine. And we're reacting with okay, so a couple things here. We have a secondary, secondary electrophile, and we have a strong nucleophile. So that's like, easy SN2 right here. What you're gonna have is your S minus is going to attack the electrophile from the back and kick off the leaving group in a single step. And as a result, your sulfur will attach over here, right? It will attach over there, but you don't even have to draw it in the back. You just know it happened there, but you can draw it here in the front, right? But you're drawing it on a dash because dashes and wedges are opposite sides to each other. So it attached to the opposite side, which is why we got the dashed version of this. So this is not possible for this specific reaction. This is not possible. So you do not form racemic mixtures. You only form a single enantiomer. So this is gone. Now, when it comes to your transition state, right, it's just like, you can think of it like this. You're losing the bond between the carbon and the iodine, and actually let's not do a dash. Let's do a like this. You're losing the bond between carbon and iodine, and you're forming the bond between carbon and sulfur. So that's like what your transition state would kind of look like. And you have your hydrogen still there. but that's like what the transition state looks like, right? Transition state. Please forgive my bad drawings. Okay, let's do another example. NaN3. N3 minus is a good nucleophile. It's strong. It's negatively charged. Right? It's N3 minus. It's going to attack this and kick this off. This time, I mean, yes, it does do a backside attack, but like, there is no stereochemistry here because this carbon is not chiral. It has two hydrogens. So you don't have to draw anything. It's fine. Okay. What about this? So this is a strong nucleophile. It's a negative phosphorus, but you need to understand that SN2 hates steric hindrance because the nucleophile is attacking the carbon and kicking off the leaving group at the same time. So if there's a lot of clutter, the nucleophile cannot reach the carbon. So this carbon right here, it's tertiary. We're bonded to 3 different carbons. Tertiaries are not going to react with, or it's not going to do SN2, right? No SN2 reaction will occur because your nucleophile just cannot reach it. If it does occur, it's very slow, but the consensus opinion for all the professors at this school is that this will not do SN2. It's either going to do elimination, which we haven't talked about, or SN1, but it's just like very like unfavorable. So keep this in mind. This will help a lot when it comes to ranking. Another instance where SN2 will probably not occur is this. Let's say I'm reacting with a strong nucleophile and doing SN2. This will also probably not occur, and if it does, it will be very slow. You have a secondary next to a quaternary. Same thing. If you're trying to come in from the back, you have all of this to deal with, right? It's hard to explain two-dimensionally, but just keep in mind, these are in the way. So it's very hard for the nucleophile to just reach this. So for that reason, SN2 will probably also not occur over here. So now, like, they might give you some question where they're like, rank by rate of SN2, rank by SN2 rate, and, they'll give you this. Okay, so number 1 will be your fastest. So let's say, this is primary, primary, secondary. This is primary, but next to a quaternary. So this is going to be rank 4. This is the worst. Now, for our 2 actual primaries, the only difference here is our leaving group. So the better the leaving group, the better, right? The faster the reaction would be. So this would be number 1, because bromine is better than chlorine. This is number 2. And then this one is secondary. It's not that bad, but primary is better than secondary. So this would be rank 3. So usually there's going to be an easy option that you know for sure is the worst. And it's either going to be this case right here, or it's going to be this, where it's right on a triple, a tri-substituted carbon. Okay, now let's talk about solvents. So SN2, it likes polar protic. Polar aprotic. And examples of this are acetone, which looks like this. There's also DMF, which looks like this. You don't have to know what they look like. I'm just flexing on you. So you have acetone, DMF, and like, I don't know whatever else there is, right? You know what I'm going to write actually? I'm going to write this. Acronym. Anytime you have an acronym like DMF, DMSO, or just something, right? it's most likely, or even like a name like acetone, it's most likely going to be aprotic if it's not nonpolar. So these will be your polar aprotic solvents. Um, Polar protic, on the other hand, these are going to have H bonding capabilities. So a big example is just methanol, right? So CH3OH or CH3NH2. These are your main polar protics. And polar protic is good for SN1. Now, a third category we did not talk about because nobody likes them is just nonpolar. So, a very common nonpolar solvent will be hexane. And what is hexane? Hexane is literally this, right? Hexane is just hydrocarbons, it's nonpolar. So, before we even talk about the polars, we can agree that nonpolar sucks for both, or for everything actually, for everything, even elimination. Because think about it. Let's say you have a reaction going on like this. These are all polar molecules. And you need, I mean, this might not make sense to you. I don't know if it will. But you need these to dissolve in order for them to react, right? You need them to dissolve. And we know that like dissolves like. So if you have a non-polar solvent, it's not going to really dissolve these. And if it does, it will take a long time. So in terms of what affects the rate, like your solvent, if you have a non-polar solvent, it's going to be pretty bad because the reaction might not even run. So that we can understand. Now what about protic versus aprotic? Okay, let's talk about SN2. What did we say is the rate for SN2? We said substrate and nucleophile. So if you affect any of these, that's going to be an issue. Okay, so let's say we have a nucleophile that looks like this. That's a strong nucleophile. And then let's say you bring in a protic solvent like this. What's going to happen is H bonding. I don't mean that the hydrogen literally bonds with the O. I just mean the IMF, the intermolecular force of H bonding, where a hydrogen that comes from either a nitrogen or an oxygen or fluorine is going to have these intermolecular forces with other elements. So in this case, it's going to affect this, right? The H bonding is going to affect your nucleophile. And what do we say? Nucleophilicity impacts the rate of the SN2 reaction. So if I'm hindering my nucleophile, then I'm preventing it from reaching my electrophile, and it's going to cause problems. So it's going to slow down the rate. For that reason, we want something aprotic. So aprotic, but still polar. So you can have this right here, cyanide, or whatever, cyanonitrile or cetonitrile is good. This is fine, right? There is no, there are hydrogens here, but these are bonded to carbon, so there is no opportunity for H bonding, right? H bonding means that the hydrogen is bonded to N, O, or F originally. So this is fine. Or if you look at this, right? Same thing. Our H's are on our carbon. It doesn't matter. Now for SN1, on the other hand, what is the rate? It's K times substrate. So there's two things that happen, right? You have your carbocation and whatever, and then you have your nucleophile. First of all, if you have your nucleophile having H bonding with the solvent, here this is our solvent, and this is our nucleophile. If there's H bonding, it's not gonna matter, like it's not gonna affect anything. It's fine because nucleophile is not part of our rate. So that's one thing you can think about. Also, I don't know how to explain this well, but the H bonding will stabilize your carbocation intermediate. I can't tell you exactly how, but it just does. Just trust me. It stabilizes your carbocation intermediate, and since our rate determining step is the formation of a carbocation, and as I mentioned at least 6 or 7 times, the stabilization of your intermediate, the rate determining step, will influence the rate of the reaction. So if you're stabilizing your intermediate, that's really good for the reaction. So that is why SN1 likes polar protic solvents. And once again, our main ones are going to be these right here, like methanol, ethanol, methylamine, etc. just something that has an H that's on an O or an N. And I don't think you'll ever see F because that's like the only way you can have that is HF. But it will be pretty chill. So one more time before we continue, I want to make something clear. If you have this and you're reacting with this, and then my solvent is CH3OH, this will still do SN2, okay? You'll still get this. But, like I said this right here, right? This is a protic solvent. I'm still getting SN2. Why? Because protic, it's not gonna like affect SN2 from occurring entirely. It's going to hinder it a little bit. It's going to influence the rate. But you can still do SN2. It's just that if I reacted with the same nucleophile, but then this acetone, I'll get the exact same product, sure, but this will be faster because our solvent is acetone. It's aprotic. But both still occur. But usually like what they do on exams is they'll give you a certain reaction and they'll be like, if I replace the solvent from methanol to acetone, what happens to the speed? And then you should know, right? Like, oh yeah, the solvent matters, like it should be aprotic. So that's something you can know, right? But I want you to keep in mind, don't look at the solvent and try to figure out if it's SN1 or SN2, because I swear to God, they did this shit on purpose. But like on my exam, they made it really confusing on if it was SN1 or SN2, and they put a aprotic solvent. So I was like, oh, this is SN2, and no, it was SN1, and vice versa. So like, don't look at your solvent to determine the reaction type. Just don't do it, okay? Because both can still occur with both types of solvents. One more thing on the topic of SN2 and the what is it's called, the stereochemistry inversion. Let's say we had this, and I protonate it. Pay attention to what happens. I'm still on a wedge. And then if I react with a nucleophile like iodine, then and only then will I invert. Same thing if I tosylate. If I bring in tosyl chloride, I'm not attacking the carbon. All I'm doing is I'm attacking this oxygen or something like that. So my oxygen will still be on a wedge because the carbon is not being touched at all. So I'm going to have this. And then once I react with a nucleophile that is actually attacking the carbon, this will lead to an inversion of stereochemistry. So keep this in mind. Okay, let's move on. E1. Honestly, like E1 and E2, we can kind of like tackle together, but let's start with E1. So E1 is kind of like SN1, right? Where you're, it's a two-step reaction, and the rate determining step is your carbocation formation. So for E1, the first thing that happens is your leaving group leaves, and then you have a carbocation. And then from here, you can bring in a base. So E1 requires like just a base, right? We're not really looking at nucleophilicity, we're looking at basicity. So the base is going to, I don't know, you can low-key just use CH3O. I don't even know, to be honest, like CH3OH or something. You can use this and it's going to extract a proton from somewhere. So before we begin, right, let me just write, I'm gonna write HB for base. Okay, I got this question by someone or a couple people where you heard about alpha and beta, right? Take a look. When you say alpha and beta, it's in relation to something. So if I'm asking what's alpha to this carbon, it's going to be the things next to it. So this is alpha, and this is alpha. But I think what some people get confused with is that they ask you in class, like, what's alpha to the bromine? The thing that's alpha to the bromine is what's directly connected. So this is alpha. And then the things after that are going to be beta. But, just keep in mind, in terms of classification, like alpha and beta, it's in reference to something. So if you hear the term, oh, beta carbons have easily extractable protons, but then someone else like me says, oh, it's the alpha protons, it doesn't matter because we're probably talking about the exact same thing, just in relation to something different. So I would low-key just not use this terminology because you're going to confuse yourself. So what I want you to understand is that the first thing that happens in elimination 1 is formation of carbocation. Then on this carbon, right, the things that are next to it, you have these hydrogens. I'm going to draw one per carbon. So you have this hydrogen, and this hydrogen. One of these will be removed, okay? What I'm about to show you does not actually occur, but it's going to explain what ends up occurring. So let's say I do what a base does, which is, steal a proton. What is that going to do? That's going to make my base happy. Then I'm going to have a negative charge here, right? Once again, this doesn't happen literally like this. It's just for explanation purposes. What can I do from here? I can just form a double bond, and that's perfectly fine because the negative charge is fulfilled and so is the positive charge. This carbon gained a bond and this formed a bond, right? So it's good. Now the reason I say this doesn't happen is because it's not that you form a negative charge. It's more of like a one-step type of thing that happens. So if you have a hydrogen here and your base comes in, it's just like all together. So your base will take a hydrogen and this bond will just form the double bond, right? So you're not really forming a negative charge, you're just forming a bond instead of doing a two-step thing, which is negative charge, then a bond, if that makes sense. So step 1 was forming the carbocation, and step 2 was stealing the H and forming that bond. So you would get this right here. However, I know a lot of you are thinking I'm stupid because you're like, this is not the right answer. That is correct. This is not the right answer. This is a minor product. I'm going to get into the actual product. I just showed this for explanation purposes. Now, it's good that we talked about alkene stability at first because that will influence your product, right? Let's redraw this. So you realize that if you do either of these, it will be the same thing. So you can either form a double bond here or on the bottom one, they'll be the exact same thing. But what if we form a double bond over here, right? What if we do that? Take a look at this. This alkene is tri-substituted. Whereas this one, it's di-substituted. And so is this one right here. It's di-substituted. And we talked about how 4 is better than 3, is better than 2, is better than 1. So that's why this will be like your major product. Now, if you do, let me think of something real quick. I don't know. I guess just say that you have this is your carbocation. Like, I don't know. Let's just do iodine here. And you're going to do a weak base. I can't really think of a weak base right now, but a weak base. Okay, first step is forming your carbocation. And, you have some good options, I guess. You can form a double bond here, which is, it's not bad. It's tri-substituted. But since it's E1 and you're forming a carbocation, you can rearrange. So what you're going to do here is rearrange it. Obviously, you're going to rearrange it 1 over. And, sorry. You're gonna move the carbocation over here. Now what happens? I can form a double bond here now, because all I gotta do is extract a proton from here. So I'll remove this, form the double bond, and boom, right? I'll end up with, look at this, 1, 2, 3, 4. That's tetra substituted. So that's where carbocation rearrangement can come into play for elimination. And same thing with elimination, like, your polar product stuff is fine. I don't really think they use that for elimination, but if they do something, it's polar product. And then E2 will be polar aprotic. Okay, so I think that's it for elimination. There's not much. You're just basically forming double bonds, and you have the carbocation rearrangement. So, once again, it's a two-step reaction. Should be exothermic, but the first step is rate determining. Second one is not rate determining. For E2, you're gonna usually have oh shit, my fault, guys. For E1, let's just write it. I think you should understand this by now, but the rate is going to just be K substrate again. So it doesn't really matter if it's, it doesn't really matter what base you have. You're just looking at the substrate. And so a lot of steric hindrance is fine because you're just forming the carbocation and ultimately a double bond. But for E2, your rate is now K times substrate times base. So in SN2, it was nucleophile over here. Now it's base because elimination deals with nucleophiles. Something to remember, all strong bases are strong nucleophiles, but not all strong nucleophiles are strong bases. Let's keep that in mind. When it comes to basicity trend, don't forget that bean thing. I hope you didn't forget it. But B is on the top left. So as you go up and to the left, you're going to have more basic things. So yeah, that's something you can use to your advantage on ranking questions, which I'll probably throw in at the end of this. But E2, okay, something interesting about E2 is that E2 requires something called anti-coplanarity. What the hell does this mean? Let's draw something out. Let's say I have a bromine on a wedge, and I have just a metal here. Okay, you would think that my E2 product should be right here. Sorry, I'm just drawing it in metal here, just to make it look better. Actually, it doesn't matter. I'm sorry, guys. I need to stop being stupid. Anyways, right? You would think, okay, the best option is here because I have 3 substituents. Whereas if I do it over here, right? If I do it like this, I only have 2 substituents. But the thing is, this is not going to occur because E2, it's a one-step reaction. It's concerted, and so it requires something called anti-coplanar, which just means opposite sides of the same plane. So for example, right, if my leaving group is on a bromine, the H I'm extracting should be on a dash, right? What is wedge and a dash? A wedge is coming towards me. A wedge is pointing towards me, and a dash is pointing away from me, right? So they're like the same plane, but opposite sides. Another way you could look at this is this right here. Let's say I have look at this. Both bromine and H are on lines. They're on the plane, but they're opposite sides. H is going up and bromine is going down. This is also a type of anti-coplanar. I'll explain why this is the case, or why we need this, but just keep that in mind what anti-coplanar means. So if you look at this tertiary carbon, you have a hydrogen, but it's going to be on a wedge. Both your hydrogen and your leaving group are on a wedge, so this is not going to occur. Whereas for this carbon, you have wedge H and you also have dash H. So E2 is going to form a double bond, but in particular, it will be over here. Now, I didn't even talk about the mechanism because I think it's self-explanatory now. You're going to have your base, so I don't know, bro, CH3O minus. It's going to extract a proton, form a double bond, and kick this off in the exact same step, right? So step 1, or whatever, part 1, sequence 2, and sequence 3, all in one step. You're taking the H, the bond comes here, and you're breaking this. That's what forms your double bond. Now, if you understand this, we can kind of take it a step further to explain why we need anticoplanar. Just look at this right here. If I have a bromine here and an H, first of all, this is a wedge. It's going up, and this is a dash. So that's the one way we can know this is anticoplanar. But even visually, they're on the same plane, right? They're on the same axis, and they're just going opposite directions. So that's anticoplanar. The orbitals are, I don't know what the hell the orbitals look like, but the orbitals are lined up very perfectly. So if your base comes in, look at this. It will take your H, form a double bond, and kick this off. Look at that. It's a straight line that's occurring. It's just so simple. That's why E2 wants anticoplanar. If you had a different scenario like this, so our H is here, and then our bromine's there, it's a little bit chaotic. I don't know how this works. That, I don't know, bro. Something like that. But the thing is, this is not going to occur, right? If it does occur, it's very, very, very slow to the point where our professors will just say, no, it doesn't occur. So you want to do it where you actually have the anticoplanarness or anticoplanarity. So another term to know is Zaitsev and the Hofmann product. Zaitsev products are going to be the more substituted alkene, and Hofmann will be the less substituted alkene. So you can kind of think of it like major and minor products, but I wouldn't use that word because sometimes your major product will be Hofmann. So for this example that we had at first, let me draw it one more time without any of the clutter. Your product, if you do E2, will be the Hofmann product, where you're going to get a double bond on the less substituted position. Because technically you can form a double bond here, that would be tri-substituted, but you just can't get it because of how the molecule is set up. And so your product in this specific case will be the Hofmann product. And then if it didn't matter, you had this, then you could do either of them, right? You can actually form a double bond here, and you could also technically do this one, but this is your major product. The Zaitsev, the more substituted, will be the major product because your bromine and hydrogen are anticoplanar. So that's something to keep in mind, right? These terms, anticoplanar, Zaitsev, Hofmann, all good things to know. Okay. Another thing is, let's say you have, I'm sorry guys, I'm getting really tired. It's like 12 a.m. So let's say you have this. And then, I don't really know. Let's do okay. Let's say you have this right here. Your first instinct might be, oh shit, my H and my Br are not anticoplanar. They're syncoplanar. They're the same side. So I'm just going to form my double bond over here, and I'll keep everything as is. However, I'm here to tell you you're horribly wrong. If you look at the ring we're forced to do the Hoffman or the Zaitsev, right? Just depending on the situation, because you can't rotate. But when it comes to these non-rings, these acyclic molecules, you can rotate. So essentially, I can rotate this such that I can make my H on a wedge. So I'm going to give you the long way and then the short way. Actually, I'm going to give you the short way, okay? This is the short way. Forget the long way, because visualization is low-key annoying. So when it comes to forming a double bond, pretend you wanted to make the Zaitsev as is, okay? As is. You put it like this. So your product would look like this right here, right? But I want you to keep in mind that this is wrong, right? When you do this method, keep in mind like what you're doing right now is wrong. Okay, what is this classification? Is this cis or trans? This is cis, large group and large group, same side, it's cis. So what you're gonna do is you're going to redraw the alkene and make it the opposite. So if your incorrect way is cis, your correct way should be trans. So you can keep one side the exact same, right? Or you can even do this side. Let's do the larger side the same. So we'll do it like this, okay? Now, instead of our thing going up, we're gonna put it down. So in this case, I'm just showing that I rotated this one. You can rotate anything, doesn't matter. But look, I made it trans. This is correct. This is wrong. Because we had to rotate this, or rotate one side, so that we could make the H and the BR anti-coplanar to each other. Let's do another example, because that was kind of fast. Okay, so you're probably wondering, oh no, what the hell do I do here? I made this kind of insane on purpose, but look, you see that the bromine and the hydrogen are not anti-coplanar, they're on the same side. So the first step, just form your regular double bond like this, okay? And what do we notice here? Are they cis or are they trans? These are going to be, it should be cis, because let's just draw this, right? Okay, so this is once again the OG molecule, not the correct one, but as you can see, the on the right side, this is the larger or the higher priority substituent. On the left side, let's see, you got carbon and carbon, and then this carbon is bonded to 3 carbons, whereas this one's only bonded to 1. So actually, it's going to be trans. So this will be trans because this is larger or higher priority. So all you gotta do here is just know, oh, it's supposed to be, it was trans. I'm just gonna make it cis. So what you can do, just rotate this. So I'm gonna put the ethyl up here and the methyl down there, right? So let's do it one more time. Let me give you once again like an easy way to do it. Forget the whole cis change to trans thing that I said. Literally draw it as is. Draw it as is. Okay. So I'm gonna have my alkene, and I have my ethyl and methyl, and down here I have 1, 2, 3 fluorine. Okay, I drew it as is. Take the easier side, so the side with less stuff, and swap them. So bring this down here and bring this up there. What does that look like? I make this an ethyl, and I make this a methyl. Boom, that's it, you're done. This is the correct answer if you're doing elimination E2. So look at this. You have a Zaitsev product. You have the tetra-substituted product, and it's possible, right? It didn't look like it was possible at first, but it is possible. So that's how you can approach these. Okay, I'll give you one more slightly easier question just for your practice to make sure you understood everything. I'll explain it one more time, and then we'll move on. What is the E2 product of this? Take a couple moments to figure it out, and let's talk about it. Very simple, right? Form a double bond. So form a double bond here. So let's take this. Okay. Just choose one side and flip it. So I'm going to choose, I mean, in this case, they're identical. I'm going to choose the right side. I'm going to flip it. So I have my original here. And I'm going to just flip the left side, I guess, right? So I got my methyl there and ethyl. Okay, this is your correct answer. It's going to be a cis instead of a trans. So that's how you do E2. Now, before we continue, okay, one more thing. We already talked about this, but if they say rank by, hold on. If they say like rank by, I don't know, speed of E2, and they'll give you a bunch of bases like right, stuff like this. So what you want to do is go up to the right. So bean trend, right? Your periodic table, you want to go up to the left. And if you look at our periodic table, it looks like this. So carbon is furthest to the left, and then we got nitrogen and oxygen. So since since basicity affects your E2, you want to look at basicity. So carbon one would be number one, the nitrogen one would be number two, and oxygen would be number three. Okay, by the way, guys, we're not done. We have one more thing to talk about. Let's erase all of this stuff. Okay. So we talked about like Zaitsev-Hoffman. There is a situation where you're always going to be forced to give the Hoffman product. That's when you have bulky bases. Bulky bases, the ones they give you are strong. It's just they're bulky, right? We know that steric hindrance is bad for the two reactions, so like E2 and SN2. So something to keep in mind, right? They're strong, they're going to do E2, but they're not going to extract a proton easily. So the bulky bases you deal with are LDA and some form of this thing right here, KOT-bu. I'm going to write this in several different ways so that you can always recognize it. So KOT-bu is negative O T-bu, which is also CH3 3CO minus or with a K, and the actual thing looks like this. This is your T-butyl part. So definitely recognize this. LDA, I don't think they're ever going to show you what it looks like, but if you're wondering, it looks like this. Or sometimes they'll put like, you know, your Na or something, right? It's lithium diisopropyl amide. So these are pretty bulky, right? They're sterically hindered. You got a lot of stuff going on here as well as over here, but they're strong. They are strong bases. So what happens is if you are trying to do E2, and let's do this. Look, your hydrogen is on a dash. You do have anti-coplanarity here. But if I'm reacting with a bulky base like LDA, then it's so big, right? This thing is so big that it can't like, it's going to be hard for it to just go through all of this. So what it's going to end up doing is going to take a hydrogen from here and then do the whole elimination stuff. So you're always going to get the Hoffman product. The Hoffman product, okay? So I'll keep this here and I'll form this. This will be our answer. This will be our major product, right? So the two times you're forced to do Hoffman, you're forced to do Hoffman if you have a bulky base or a ring, I'm not going to write this whole, but a ring in which your Zaitsev is not possible due to lack of anticoplanarity, right? So in case you don't know what I mean, let me write it one more time. Where if you have this, I'm just going to react with a regular strong base, like KOH. If I'm reacting like this, it's not bulky by any means. It's a normal strong base, but I'm in a ring, so I can't rotate any of these to make them anticoplanar. So I'm forced to do the Hofmann product over here, right? The other case is what we just talked about. We do have anticoplanarity here, but since we're using a bulky base, we can't reach that good hydrogen, so we're forced to do the Hofmann product. Okay? I'm trying to make sure I didn't miss anything. I think we're good. I covered like most of the stuff. I just want to talk about one more thing before I'm done with this. I don't know how long this video was, probably like 2 hours. But this is about how to approach synthesis, okay? Here's the thing, synthesis is going to be part of organic chemistry for the rest of your life, or for the rest of your time in this class, for OChem 1 and 2, and it's only going to get worse from here. Like, you have it very easy right now because you only know a select few set of reactions, so there's only so much you can do. But in the future, you're going to learn so many reactions that you're going to have like to figure out which of your 2,000 reactions apply to different scenarios. But as of right now, you only really know like 4 or 5 reactions. So it should be pretty straightforward, okay? Let's start with number 1, or this first one. I want to mention real quick, the reactions you know are halogenation or monohalogenation. And then you have your SN reactions and E, right? So it's just going to be a mix of these. That's really it. That's all you got. So what I would do is honestly just work backwards. That's what I would do, to be honest. So for this first one, you could say that bromine is it got monohalogenated or something, right? So I would go backwards and be like, okay, look, I could be wrong, by the way. Bromine is also it can be a strong nucleophile, but test out different things. I'm just assuming it was a radical at first, right? So I'm gonna be like, okay, it was this, right? It was a radical. We can just even draw it without the radical. Like what I'm trying to say here is that, oh, we brominated this using NBSHV, which would give you this product. So I'm gonna be like, okay, we have that. And then what happened? Okay, when it comes to alkenes, I know how to make alkenes. There's a couple of different ways we could do this, but it looks like, it's a Hofmann product, not a Zaitsev. So I'm gonna draw my molecule, and I'm gonna just say that I had like, I don't know, like a bromine here, and I did a E2 reaction, right? I can only form a double bond here because it's primary, so that's some way you can think about it. But then you're probably wondering, okay, how do I go from there to there? You can't just do Br2 because your bromine would attach here. Okay, so there you go. Look, I was wrong, right? This is kind of how you want to like think about it. You want to work through it. So now I know, okay, my bromine must have been here. My bromine had to have been here because that's the most substituted position. So then how do I get a Hofmann product? We talked about this. You want to do a bulky base. So you want to use this right here. KOT-bu. Okay, cool. This will do E2, but it will give us our Hofmann product. So we don't have to worry about getting a product that looks like this because it's going to do the less substituted side. So it's much easier for it, right? So this makes sense now. And then as we talked about, how do we go from the first to the second step? Br2, Br2HV, because the bromine will attach to the most substituted carbon. So do you see this like workflow? That's kind of how you want to think about it, right? And as I made a mistake, right? I made a mistake, potentially on purpose, because I want to show you, like, you're probably not gonna get it the first try. If it doesn't make sense, you're good. You're probably wrong, and so you can try something else. Okay, let's do the second one. So first thing I noticed is that our carbons are in different locations now. So what I recognize is that a carbocation shift happened somewhere. So I'm going to keep that in mind because an SN must have occurred. I also noticed that there's a whole oxygen, a methoxy group, sorry, an ethoxy group added. There is no double bond. So I had to have done SN1 in particular because one, there's a carbocation shift, and two, there is a whole like addition of a group, right? But please remember, okay, please remember, in order to do any substitution, you need a leaving group. And you know how to make a leaving group, which is monohalogenation. So this time I'm not even going to work backwards. I'm just going to work forwards. The only thing I can do here, like literally the only thing that you know how to do at this exact moment is monohalogenation. There's nothing to eliminate. There's nothing to substitute. So you either leave it as is or you monohalogenate. So I don't have to work backwards. I know this is the first step. If I'm wrong, that will be very pathetic. But anyways, right? There is no rearrangement or anything. I just put a bromine here. Okay, then how do I go from here to here? This is just going to be one reagent. It's 2 steps, but let's low-key just take it 2 steps. The first step, I'm about to throw something crazy at you that you don't recognize. It's AgNO3. I'm glad I brought this up because I forgot. AgNO3, if you ever see it, all it does is it forms a carbocation, like it allows your leaving group to leave. So what this will do is here, it's just gonna do this right here. It's gonna allow your bromine to leave and form a carbocation. Then I know that there had to have been a carbocation shift because there's 3 methyls here, so there's no way that an alkoxy group can attach to it. And it makes sense, right? We're secondary, so we can do a carbocation shift and do a methyl shift in particular, and that would look like this, right? Where I do a methyl shift. I'm gonna call it M shift. You don't have to write this, but I'm just writing it just so you're aware. And then from here, I did a this, right? It doesn't matter. You can do O minus or OH because we already have our, carbocation formed, but that's how you would do it, right? So let me do this one more time just because it was a little bit confusing how I explained it. You can straight up do, you can write it like this, right? You can write 2 steps in the same thing, AgNO3 CH3OH. Or you don't even have to do that. You can literally just write CH3OH. But I'm bringing up AgNO3 because if you ever see this, just know it makes our leaving group leave. So if you did AgNO3 and CH3OH or just CH3OH, you would get the same thing. I think this is one of those things that experimentally allows the reaction to happen better or something. I don't know. But yeah, this is what you do. So one more time, as we talked about, what would happen is your carbocation would form because your leaving group leave, and then or left, and then you'd have your methyl shift, and then your OH will attach, and then you'll have workup, right? That H will just leave, and you'll have this as your final product. Okay. I really hope I didn't forget anything because I really don't want to re-record this, but as I always tell everyone, everything I talked about today is content, but the best way for you to actually retain this information is to practice. So you can refer to this video to learn things or clarify different concepts, but unless you practice, you're not going to remember all these things, right? You're going to see so many different scenarios and types of questions that I may not even have covered, or you may not even have like thought of based on how I explain things. But when you come across these questions and you apply what you know or learn what you don't know, that will be the best way for you to learn. Okay, so I hope this helped. If you have any questions, let me know. And yeah, I think I covered everything, but if I didn't, you can always ask me questions. Peace out.